Hi everyone, and welcome to the last lesson in Unit 4. Today we'll be talking about the mean value theorem for integrals and average value. So if you think back to lesson 3, that's where we saw, in Unit 4, that's where we saw how an area under the curve was underestimated oftentimes, most times, by an inscribed rectangle. And that's when we ended up with negative error. But when we use circumscribed rectangles, typically the area was overestimated and we ended up with positive error. So if you think about, and one thing we saw when we did a midpoint approximation is that oftentimes we can balance out that negative error with the positive error. Well, that's sort of the idea behind the mean value theorem for integrals. Basically what that states is that somewhere between the two scenarios of inscribed rectangles and circumscribed rectangles is going to lie some kind of balance where the rectangle has an area exactly equal to the area under the curve. So what the theorem actually states is if we have a continuous function f on the closed interval from a to b, then there exists, remember that backwards e, that means there exists. It's one of the quantifiers in math. There exists a c that is an element of the interval from a to b. So c is going to be an x value in the interval from a to b. Then what we have is that the definite integral from a to b of the function f of x dx is equal to f of c times b minus a. Now think about what all these pieces mean. The integral from a to b of f of x dx, that's the area under the curve, a definite integral. F of c times b minus a, well, that's going to be the area of the rectangular region. F of c is going to be the height. The height of the rectangle. B minus a is going to be the base, the width. So it's an interesting idea, and on the next page you'll see also in your hand a graph of this. One thing to note is that the value of c is not necessarily unique. There can be more than one, just like we saw with the mean value theorem really for derivatives. Back in, I guess it was Unit 2 it might have been. This also is an existence theorem, just like the original mean value theorem was, meaning it just tells us that the c value exists. It doesn't so much tell us how to get it, although the formula pretty much leads to how we get it. You might remember back to the mean value theorem, the original one, that's the one that states that somewhere on a curve, once again we had a continuous curve on a closed interval from a to b, that somewhere on that interval, remember, there would be a place or places where the derivative, the slope of the line tangent to the curve, was equal to the slope of the line that connected the endpoints. So let's take a look at a graph that gives us a really good visual of this. This is the one that I really like to use a lot. All right, we have the function f of x. And if you think about what the theorem states, we're assuming it's continuous. Here's our interval from a to b. So what this is stating is that somewhere in between a and b, we should be able to find a place where the height of the rectangle, right there, height is given to us by f of c, times the width of the rectangle. And the width of the rectangle is always going to be from a to b. That area of the rectangle is going to be exactly equal to the area under the curve. So what you see here, the shaded region in gray, that's supposed to, in the end, be equal to this area under the curve. All right, and if you take a good look at it, and And we did as good a job as we could at drawing this. We talked about, inscribed rectangles often giving us an underestimation and therefore negative error. Circumscribed rectangles giving us an over approximation of the area and therefore positive error. This is really truly finding a balance between the two. What should theoretically happen if this was drawn actually totally perfectly, this positive error here is offsetting this negative error here. Okay, and that's really what should happen. And if you remember back, that's what we often found when we drew for ourselves a midpoint approximations with rectangles inside a curve. So the area of the rectangle, really, that we're setting equal to the integral is going to be the width of the rectangle given to us by b minus a times the height of the rectangle given to us by f of c. So let's take a look at a couple problems. So we want to find the value of c satisfying the mean value theorem for integrals on the interval from 1 to 3, and our function will start out with an easy one of f of x. All right, so let's go ahead and set it up. So what the theorem states is that the integral from 1 to 3 of the function, that should equal to, remember we're setting it equal to the area of a rectangle. So the height of the rectangle is f of c. The width of the rectangle is going to be the difference between b and minus a. All right, so essentially what we have is the integral is equal to 3 minus 1 obviously is 2 times f of c. All right, so we can go ahead and evaluate that definite integral. You can either do that by hand or you can do it on your calculator. Either one is fine. Remember, if you're doing it by hand, it's going to be 1/3 x cubed, and you're going to evaluate that from 1 to 3. 3 cubed is 27. A third of that is 9 minus a third. So we have 8 and 2/3. So what's that? 26/3. So that's equal to 2 times f of c. Now in place of f of c, remember we're trying to find an x value at which this is going to occur. So if you want, and we did this, you might remember with the mean value theorem, in place of f of c, we're just going to put the function. And we're going to go ahead and solve it. So we'll divide both sides by 2. That gives us 26 over 6. Obviously, you can simplify it. So that's equal to x squared. So we'll take the square root of that, which you can just do on your calculator. So we get plus or minus 2.028, or 82 rather. Remember that our value has to be within the interval from 1 to 3 in this case. So in this case, our c value that we want is going to be that positive 2.082. So it kind of looks similar to the original mean value theorem and how that we were always solving for an x. We wanted to see what the x was at which all this would take place. So let me draw a picture of this for you. And hopefully that, I think drawing the pictures really, really helps. So let's see. I think I can fit it up here for you. 1, 2, 3. So let's see, we have 0, 0, 1, 1, 2, 4, 2, 3, 9. So it's your, obviously, typical parabola. Okay, so here's our function. So what we just found is we know the rectangle is going to go from 1 to 3. So here's the sides of the rectangle. Okay, what we just figured out was C was 2.082, so that's going to be a little past 2. So if we trace that up to the curve, right, that now becomes where the height of our rectangle is going to be. All right, and that's the green rectangle is the rectangle that if you were to find the area of it, that is going to exactly equal the area under the curve, x squared from 1 to 3. And again, if you take a look at it, let's see if we kind of drew this dotted line. What should be happening is this area here is offsetting this area here. I didn't do too horrible a job drawing that. Right, but that's really, it's kind of an interesting idea. You're finding an area under the curve, but someplace there should be that like balance point. That's sort of what C is, that, at that point, if you created a rectangle out of it, the area of the rectangle is going to be equivalent to the area under the curve. It's kind of a cool idea. So let's try another one. So let's do a trig one. So we want to find the value of C satisfying the mean value theorem for integrals on the interval from 0 to pi if the function is sine of x. So once again, we'll set it up as the definite integral from 0 to pi of sine of x dx. And remember, you're setting that equal to the area of a rectangle. So the height of the rectangle is f of c. The width of the rectangle in this case is going to be pi minus 0. So once again, you can either evaluate that integral by hand, or you could do it in your calculator. Remember, antiderivative of sine is going to be negative cosine, and we'd be evaluating that from 0 to pi. So let's see, negative cosine of, that's going to be a positive 1, minus another negative 1, so that turns into 2 when you do it. Feel free to check it on your calculator if you don't believe me. So pi minus 0, of course, that's pi, so that's the width of the rectangle, and we're going to have that multiplied by f of c for the height. All right, so coming down here, we have pi. In place of f of c, we're going to put sine of x. If you care to put sine of c, if you find that easier, that's fine. You might remember we came across that before when we did the original mean value theorem. So we'll divide both sides by pi. This is one you might want to solve graphically. Put like this part under y1, do this under y2, find the point of intersection. That's what I would recommend. You do get two answers. You get that x is about 0.690. Please do give it a try. Remember, these are all radians because we are taking sines of angles, so just in case you're curious as to units. The other one is 2.451 radians. You don't necessarily have to indicate radians, it's understood. Now remember, your decided upon C value does need to fall within the given interval, and in this case they both do. Remember, of course, pi is 3.14159. So this is one of those cases in which we have two answers for C. Remember that we had mentioned before that C is not necessarily unique. So this is a great example in which you do end up with two possibilities. So the way in which you go through these, it's the same thing every time. You're just setting the definite integral equal to the setup for the area of that rectangle, base times the height, and just solving it out. And that's it. So the last idea we're going to talk about today really comes from the mean value theorem for integrals, and it's an idea called average value. This is one that you'll be seeing a lot, especially as we start talking about some of the AP accumulation problems. This is very, it shows up a lot. Let's just put it that way. It'll show up on the multiple choice in the AP exam. So it's a big topic we'll be talking a lot about. So really what the average value is if you go back to what we just did, it's the height of the rectangle. That's it. So we could easily go back. So all these things we found for the height of the rectangle, that's your average value. So like back here on the sign problem we did. All right, the average value, remember, is given to you by f of c. It's the height of the rectangle. So basically, right here on this line, sine of x, all right, that's how we denoted the height of the rectangle, right? Notice how it's equal to pi over 2? That's your average value. It's really just the numerical value of the height of the rectangle. That's it. Back on the other one, back up here. The height of the rectangle, remember that was given to us by x squared, f of c. Right, f of c is always your height of the rectangle, so that's really just the function. So right here, 26 over 6, that's your average value. And if you think about it, because remember we drew the picture for this one, if you do 26 divided by 6, what do you get? 4 point something? I know it's 4 point something. 26 divided by 6 is 4.3 repeating. Take a look at how high that rectangle ended up being. Here's 4 right here. All right, and just, I didn't do a really bad job drawing that. So it really is just the height of the rectangle. That's it. That's what average value is. So therefore, it's really not hard to find because you kind of come across it as you're doing the mean value theorem for integral problems. A lot of people will just treat them as one and the same problems, and just when they get to the point that they have the function equal to a numerical value, that's your average value. Done. You easily could set up the problem like that. One thing to note, because a lot of people think, they hear this average value, so when they think average, they think, mean, add the two together, divide by 2. That is not necessarily true. All right, you cannot just take f of a, f of b, add them together and divide by 2. That is not the average value. All right, there's a very, very specific application for this, and it's very much in the context of the problem. So anytime you hear average value in calculus, you should be thinking this. The mean value theorem for integrals, and how average value is really just the height of the rectangle. So by the official definition, that's what you see down here in the third bullet. If a function is integrable, so meaning you can take the integral on the closed interval from a to b, then the average value of the function is given by, really it's just if you take that mean value theorem for integrals and rearrange it, you come out with 1 over b minus a times the definite integral. Now, as I said, a lot of people just like to think of it as, when you go ahead and set up your mean value theorem for integrals problem. All right, remember the height of the rectangle is your average value. So it's kind of like you're doing the average value times b minus a. So if you divide both sides by b minus a, that's where that formula comes from. So that's where I was saying earlier that a lot of people don't like to even bother memorizing this formula for average value. They just think of it as a mean value theorem for integrals problem. And, they know that this part for the height of the rectangle, that's your average value. And there is an average value program on your calculator. We're going to go through that today after we go through the next problem. So you'll definitely want to have your calculators handy. So let's take a look at that problem, then we'll talk about the calculator program you have. So we want to find the average value of 3x squared minus 2x on the interval from 1 to 4. All right, so if you want, like I said, a lot of people just prefer to set it up as a mean value theorem for integrals part. So we're doing the integral from 1 to 4 of 3x squared minus 2x dx. So we're setting that equal to f of c, which is our average value, times b minus a, so that's 4 minus 1. So the integral, if you want to do that part, the definite integral in your calculator, feel free. If you do that, you should come out with 48 if you want to give it a try. So 4 minus 1 is 3. So if we divide both sides by 3, we get 16. So that's your f of c. That's the height of the rectangle. That's your average value. So what that means is if we were to draw this out as we did the other mean value theorem for integrals problem, if we had drawn this out, the height of the rectangle is going to be 16. Now another thing that you could be asked for is to find where the average value occurs. You probably noticed where you've been using AV for average value. So this is a really common problem, and you do have to kind of keep your eye out for the difference between actually finding the average value and finding where it occurs. If they want to know where it occurs, that's pretty much just finishing out the mean value theorem problem. All right, so essentially, if you think of what you would have done if we had continued with the mean value theorem for integrals problem, from this step, we would have had 16. Remember, in place of f of c, we would have put the function. And then we'd want to go ahead and solve that. So we do have a quadratic, so we could go ahead and factor it. We haven't factored in a while. Let's go ahead and do that. So let's see, 3x, x, I know we're going to have a plus and a minus, so what's this, plus 2, minus 8, see, does that work out? We got negative 16 in the back, we got a positive 6, negative 8, that makes negative 2, perfect, okay. So this leads to our c values. So for our c, well, let's do our x's first. So we have x equals 8/3, or x equals negative 2. Remember, though, our c value has to lie in between 1 and 4. So the c value for this would be 8/3. Right, that's where the average value would occur. So that's why these two topics always go together. You know, you always learn about average value when you do the mean value theorem for integrals, because average value really is just one little piece of that mean value theorem for integrals problem. So I think I left room, we could draw a picture of this one if you want to see it. Let's see. I had already done this, I admit. But you could easily graph it in your calculator. Then we'll turn to the average value program. So let's see, 1, 2, 3, 4. I think I did 5. So here's 10. Oh, that's 20. Can't count. Okay, that looks good. So let's see. The points I know when I had graphed this before, it starts at the origin. And let's see, we have one at 4, 40, I think it is. But otherwise, it looks like a parabola, so it kind of goes like this. All right, that's our function. So if you go back to what we found, the height of the rectangle came in at 16. So that's going to be like right around here, would be 16 maybe. Okay, so the interval went from 1 to 4, so here's the sides of your rectangle, and we want the top to be up here at 16. So like right around there. Okay, so the height of your rectangle, that's your average value. And remember, the other thing we found was where it occurs. So take a look at how this worked out. If here's the point of intersection where the top of the rectangle cuts through the curve, if we drop this straight down, that's where our C should be. And if you take a look at what we got for our C, it was 8/3, so that's at 2 2/3 about. And that's pretty close. It's not too bad. Mine looks more like 2.5, but it's not too bad. So that's really what you just figured out. All right, and that's why, as I said, mean value theorem for integrals and average value always go together. All right, so let me show you the calculator program. And we can start with this one, then maybe we can go back and I'll show you the other ones as well. So if you have your calculator there, let me switch over to that. Let's use this last one as our first example. So what you want to do is go under y equals and just graph the function. So 3x squared minus 2x. And we can just go ahead and like zoom 6 to get a good graph of it to start. And we know it's going to be a parabola. You don't have to worry about the window. The program actually takes care of all that for you. All right, so to run the program, if you hit your program button, it's the one that looks AvgValue, that one. AvgValue, AvgValue. We abbreviate everything. You guys know that. So when you run the program, notice it asks you for the b value first. Every single year I say I have to rewrite this to flip around the a and the b, but I still haven't done it. So just take note they're asking you for b first. Okay. This is, I think, one of the programs I helped to write. A friend of mine and I wrote one at my last school. So you just enter the a and b values, hit enter, and you'll notice that it's going to redraw the graph for you. All right, what it's doing when it redraws the graph is it's actually making use of the actual calculator window as your rectangle. All right, so when you're looking at your calculator window, the left edge of your window, that is your A value. The right edge of your window, that is the B value. All right, so what you're looking at right here is the exact width of your rectangle, in this case from 1 to 4. Okay, now notice the little wormy thing is still going in the top right. All right, that means it's still working, so hit enter. It's now drawn for you the top of the rectangle. All right, so that black horizontal line, that's the top of your rectangle. The calculator window screen actually creates the rest of the rectangle, the left and the right sides, and then the bottom. And if you take a look at it, you know, we do have like this area here should be offsetting this one over here. That's the positive and negative error balance that we talked about. All right, now you'll notice your wormy thing's still going because it's going to actually give you the answer next. If you hit enter, there's the average value. All right, now it does not tell you where the average value occurs. One of these days I'll get around to writing a program that does that. I just haven't gotten to it yet because it would be pretty easy to do, actually. It wouldn't be a stretch. But that's your average value. You often see this on the AP exam and the multiple choice. It oftentimes does show up on the calculator part, so you're most welcome to make use of the calculator program. All right, so why don't we go back and maybe backtrack, and I'll show you some of those other ones. Let's do that trig one, if you go back to there. So go back under y equals. Let's change this to sine of x. That's what that function was in the second one we did. And to just set it up, I'm just going to do zoom trig, just kind of start it out with a window. Now, one thing you're going to notice that I was going to tell you about, when you're done with the average value program, you have to remember to turn your axes back on. That's another thing I will write into the program someday when I get around to it. So I'll show you how to do that at the end. Okay. So here's the function. So let's see, that interval was 0 to pi. So let's go ahead and run the program. Just hit enter. So b value in this case was pi. A was 0. All right, so remember what it's doing. It's drawing you the graph, and the left and the right edges of your calculator screen, they correspond in this case to 0 and pi. So that's the width of your rectangle. So it's still working, so hit enter, and here comes the top that creates your rectangle. And this was one we hadn't looked at a graph of, so this is kind of good to look at it. So this whole area, the rectangle, all right, here's the black line's your top, the left and then bottom and right, they're your sides of the rectangle. So take a look at what should be happening, because the area of this rectangle should be that area under the curve. So what should happen is like this area on the left, that kind of triangular part, this area on the right, that other triangular part, and then this part up top, they sort of should balance out each other in the end, all those areas. Sort of like we've been talking about in the last lesson, how the areas like above and below the x-axis like offset each other. This is a very, very similar idea. So hit enter again. Notice that the average value comes out as 0.6366. The average value as we had it was 2 divided by pi, which if you do that out, notice you get really the exact same thing. Kind of interesting how it works. So let's go look at that first one, and then we'll be all finished. So let's get rid of this. That was just plain x squared that we had done originally. So let's go ahead and change our graph. Just do zoom 6 to set it up. So if we run the program, let's see, B was 3 in this case, A was 1. So here's the curve. Remember, it was just a parabola. This is one I drew for you. Hit enter again. Here's the top of your rectangle. This one looks a little bit nicer than mine. This triangular region over here, that area is going to offset this positive error up here in the upper right. Hit enter again. There's our average value. Remember, we had figured out it was just a little bit bigger than 4. So there you go. It was 13/3, I think it was. Okay, so that's how the average value program works. If I get a moment to rewrite it, I'll let you know. It's one of those, it's not a hard program. It really isn't. I just need the time to play with it. So let me show you how to turn your axes back on. All right. What you'll want to do is go under its second zoom. It says format over it. So if you do second zoom, you'll notice the fourth line down is axes on, axes off. That's where you have to change it. Please do remember that, because if you're in the AP exam and you go to use this program and then you forget about how to turn your axes on, there's nobody to ask. Okay, so please do remember, like I said, I really want to kind of rewrite the program when I do to make the last step be to turn the axes back on, but I have to figure out a way if that can even be done. Because you have to be totally done with the problem, so, you know, we have to think about that one. But that's where you turn the axes back on. Okay? All right, so the problems that are going to be associated with this that I'd like for you to do tonight are those. The first one's on page 373. They're all mean value theorem for integral problems. The other ones on page 388, 389, they're all average value and other average problems. So pretty much involving average value. But this will start giving you a glimpse at some others that you might see. You might have to think about them a little bit, okay? So just a word of warning. We can go over them when I see you next. But definitely, you know, the ones on 373 are really, really straightforward. A couple on towards the end on page 389 you might have to think about. All right, so please do think about them, because, you know, we're trying to gear you up, and, you know, not everything right at this point and here on out is going to be exactly as we do in class. You have to start thinking on your own, okay? So thanks for watching. I greatly appreciate it. Go ahead and get your work done, and I'll be seeing you real soon. Take care.